Once again, welcome to the exciting topic of pole placement. In this presentation, I will give the basic design. We will discuss how to specify a reference model. We will cancel good and bad factors, and we will design a controller through Aryabhata's identity. We will now introduce a reference model. Let's suppose that we have this transfer function g of z given by z power minus k into b by a. This is in discrete time. You have k samples of delay. These are all polynomials in z inverse, although I just write as b of z, a of z, and so on. In addition, we assume that a and b do not have common factors. We call that coprime. Suppose that we want the plant output y to be related to the set point r, the reference signal, as the following. Here is the relationship. Because it is a model, we are calling it as y sub m. I have given it in z transform. It has the same delay. Remember, the closed loop system should have at least the same delay as the open loop system for the controller to be realizable. So we assume the same delay, z power minus k. And what is this phi CL? Can you guess this? Recall that we could choose this as the characteristic polynomial from the desired region analysis we discussed in the first part. And what is gamma? Gamma is a scalar. It is chosen so that at steady state this ym, the plant output, will be equal to the reference or the set point signal. What does it mean? It means this transfer function should be 1 at steady state. In other words, this gamma should be the reciprocal of this at z equals 1, because at z equals 1 you don't have to worry about this. It is just the reciprocal of this factor, so we get this term. Let us recall the 2DOF controller we presented earlier in the first part of this course. The only difference is now we have gamma. You can of course guess that we have this gamma because we used it in the previous slide also. And notice that we have this u, the control effort u, is composed of a signal from here, which is given by this, minus the second signal, that is the feedback transfer function multiplying the plant output y. And of course, as before, we need to determine RC, SC, and TC. These are the polynomials that appear in the controller equation. As before, SC by RC stabilizes this loop, and it also rejects the disturbance that might appear in the plant output y. And TC by RC helps track the reference signal so that this y could follow this R. For this system, we will determine the closed loop transfer function. Let's evaluate plant output y. Y is equal to what we have in the numerator divided by 1 plus product of these two. So I have multiplied the gains of these two. I have written it here. Of course, I am writing this without explicitly stating the argument z times whatever we have in the front. This is the closed loop expression for the plant output y. Let us simplify this. It is easy to arrive at this expression. I would want you to pause the video here and check that you indeed get this expression. So we have ARC plus Z inverse K into BSC. Of course, we have seen this kind of simplification earlier in the first part of the course. Alright, let us start with the expression we obtained in the previous slide and then let us equate it with the reference model. We would want this y to behave like the model output ym given earlier. Notice that we have gamma here and also gamma here. So let us equate the two and cancel common factors. We can get rid of gamma z power minus k. So we equate this transfer function here and here, we get this expression. We expect some cancellations between numerator and denominator. So as a result, we expect the degree of BR to be less than the degree of B. That is one reason why we have written it as BR. You can think of this R as reduced as well. So now we will introduce the notion of good and bad factors. This is the equation we had in the previous slide. Now let us factor this polynomial A as bad and good factors. I have the superscript B to denote bad and G denotes good. What is bad? We could think of it as a factor that resides outside the unit circle. For example, we will take an example. Suppose A is a polynomial with 3 factors as given here. Then the bad one is given here, the first term here. What is the reason? Can you find out for what value of z this term becomes 0? It's very easy because you have z coming in the denominator, you have z to the power minus 1. So this factor will become 1 when z is equal to 1.3678. Okay? In other words, we say that this factor AB has a 0 at 1.3678. In fact, from now on, whenever you see a factor like this, you should immediately see this to be the 0 of this term. So the 0 of this term is 0.7311. For the third term, it is 0.3679. We call it AB because it has a 0 outside the unit circle. Whatever is left after that is considered good, so we call it AG. You might have guessed why we defined good and bad factors. It is because we can cancel the good factors. Let us start with the expression we had in the previous slide. We split A as good and bad, similarly B also as good and bad. After that, also define our controller polynomials TC as AG_T1, RC as BG_R1 and SC as AG_S1. These are the terms that appear in this closed loop expression. Let us substitute these expressions in the top equation for controller as well as the plant. So for B we substituted bad and good, similarly for TC, for ARC term, then BSC term. Of course nothing happens in the right hand side. Now let us cancel good factors. This BG will cancel this BG and this BG. This AG will cancel this AG and this AG. So we have ABR1 and z power minus k times BB into S1 equals BR by phi CL. Now we will resort to the familiar Aryabhata's identity. Let us recall from the previous slide the equation we obtained. Let us equate the numerator and denominator. So we have BR equals BB T1. What about the denominator? So the left hand side is given here. On the right hand side we have phi Cl. The second equation is the well known Arya-Bhatta's identity. We have seen it before. Other names are Diophantine equation and Bezout identity. This equation can be solved for R1 and S1, and of course we have to assign a value for T1. Often we choose T1 to be 1, other options are of course possible. With this we have designed the controller, because the controller is given in terms of TC, RC and SC. R1 and S1 have been obtained from Arya-Bhatta's identity, and AG, BG are known from the plant model, because these are good factors of plant polynomials A and B. So let us summarize what we have seen so far. Here is the reference model. We were given rise time overshoot, so we determine the characteristic polynomial. From the steady state condition we determine gamma, and the controller is given here, and we factored A and B into good and bad parts, and we got controller polynomials. We solved Arya-Bhatta's identity. We chose T1 equals 1. The moment we chose T1 equals 1, BR equals B. It is easy to see this. In fact, if you do not remember, you have to go back and check this. We will now verify whether this solution indeed gives the closed loop transfer function as we desired here. We will do this in the next slide. So here is the 2-DOF controller, and we have put BG, BB and so on here, where we have substituted for TC, RC and SC as given in the first line. Let us evaluate the closed loop characteristic polynomial, which we denote as T. T equals whatever comes here is written first, and then what appears in the forward path comes here, then 1 plus the product of these two, 1 plus product of these two transfer functions. So let me simplify this. It is easy for you to verify this. Basically I have cancelled the good factors here, then multiply both numerator and denominator by AB R1, I get this expression. Now I cancel this R1 and this R1, I get this expression. And this is nothing but the model that we wanted earlier in the reference model. Remember, this BBT1 was BR, and the denominator is indeed phi Cl as we used in Arya-Bhatta's identity. There is a limitation as well in the form of closed loop zeros. So let us see this. The desired closed loop relation is given here, and this is as per our YM model, and this is nothing but this expression where we have written for BR, it is BB into T1, the numerator we retain as it is. So we have substituted for BR as BB T1, and what is BB? What does this B denote? This means it is the bad part of B that has a factor outside the unit circle, whose 0 is outside the unit circle. So this is a bad part of the numerator of the open loop transfer function B. So that appears in the closed loop transfer function as well. So if BB is not equal to 1, then it will always appear as a part of the closed loop transfer function. You cannot do anything about it. So in other words, the bad zeros of the original transfer function cannot be changed by feedback. This is one of the limitations of this design. With this, we have come to the end of this presentation. We will see applications of this controller design in the subsequent videos. Thanks for joining.